We say the SDN architecture supports network programmability. But once the control plane and the data plane are separated on the network device, how do you really achieve that? What sort of APIs are required? Let's find the answers in this knowledge spark. By the way, if you missed the discussion on telco softwarization so far, you can always go back and check our previous videos. Even though we know now what is SDN, it is worthwhile to look at the proper definition of SDN. Open Networking Foundation, or ONF, defines SDN as the physical separation of the network control plane from the forwarding plane, and where a control plane controls several devices. As we already know, we identified 3 layers in the SDN architecture. The application layer has the business applications. In the control layer, the SDN control software is running and different network services are available. In the infrastructure layer, you find the network devices. The 3 layers are physically separated and you need some sort of communication between the layers. This is achieved using different interfaces between the layers, and as we talk about programmable networks, these become APIs or application programming interfaces. However, the control data plane interface is different and we run specific protocols in this interface. While there are multiple options, OpenFlow is the first standard communication interface defined between the control and forwarding layers of an SDN architecture. OpenFlow allows direct access to and manipulation of the forwarding plane of the network devices such as switches and routers, both physical and virtual. OpenFlow is a vendor neutral and works on top of TCP/IP using TCP port 6633. According to ONF, the SDN architecture has some key features. Let's look at them one by one. First, the network control is directly programmable because it is decoupled from the forwarding functions. Second, it is agile. Abstracting control from forwarding lets administrators dynamically adjust network-wide traffic flows to meet changing needs. Third, it is centrally managed, as the network intelligence is logically centralized in software-based SDN controllers that maintain a global view of the network, which appears to applications and policy engines as a single logical switch. Fourth feature is the ability to programmatically configure the network resources. SDN lets network managers configure, manage, secure, and optimize network resources very quickly via dynamic, automated SDN programs, which they can write themselves because the programs do not depend on proprietary software. And finally, it is open standard based and vendor neutral. When implemented through open standards, SDN simplifies network design and operation because instructions are provided by SDN controllers instead of multiple vendor-specific devices and protocols. If we go back to the SDN architecture we discussed in our previous knowledge spark, we can now clearly see the 2 interfaces. These interfaces are classified with respect to the control layers towards north of the controller and towards the south of the controller. These interfaces are the realizations of abstractions we discussed earlier. The control abstraction gives the global view of the network, and the forwarding abstraction is realized using match action tables. What is a match action table? To understand that and the requirement of such a table in the forwarding layer, let's look at some other tables we already know. If you closely look at how an IP packet or an Ethernet frame or an ATM cell or an MPLS frame is forwarded in the forwarding plane of a network device, you understand that it is done by a table lookup in the forwarding plane. The table could be manually or automatically built using the help of the control plane. For example, take the ARP table in your computer, or the MAC address table in a switch, or the IP router table in a router, or the MPLS label table in an MPLS switch, or even an ATM routing table in an ATM switch. In all these places, you get a table. For example, you get IP to MAC mapping in an ARP table, MAC address to port mapping in a MAC address table, destination IP to outgoing interface mapping in a routing table, incoming label to outgoing interface mapping in an MPLS switch, and incoming link to outgoing link mapping in an ATM switch. Similarly, we need a table in the SDN network device. Let's take an example where our southbound interface is running the OpenFlow protocol. So, we have our OpenFlow enabled network device or the forwarding plane and the SDN controller running the SDN control software or the control plane. As there is no intelligence in the forwarding plane now, the OpenFlow table is empty. Therefore, there are no match rules to match or match actions. Once we enable OpenFlow protocol between the control and the network device, depending on the program, the required entries are sent by the controller to the network device as an instruction set. Now we have a set of match rules and corresponding actions. The matching is done top to bottom, and a packet can match only one rule. As you can see, the default rule action is sent to controller. That's it. It's simple. The same principles still hold. To forward a packet received on an ingress interface, you still need an instruction set in the data plane. The control plane helps you to build that instruction set using southbound protocols like OpenFlow. I'm sure now it is clear to you the requirement of having an API or application programming interface, or simply an interface between the control plane and the data plane in an SDN architecture. That's it for today. We'll see you soon in another episode on Telco Softwarization and looking at another aspect on SDN.